Yo, what's up, everyone? Good morning. Hope you're doing well. And um, here we are with our second problem set for this week. Um, okay, just setting, just setting up. It's earlier than usual. That's why it's kind of dark. But yeah, I don't really have any more announcements to say other than we're in a new unit, which is exponents, which is something that I personally really enjoy. And I think this won't be too long of a lesson, but I think it's going to be pretty satisfying. So all we've been looking at in the last worksheet was we've been doing sequences, and we started to take the sequences and turn them into graphs, right? And we know a sequence is just like a set of numbers that has some sort of pattern. So our last unit was we would basically do a bunch of math with sequences. But what we're doing now is we want to realize that a sequence and a table are kind of the same thing, right? Where these are five numbers, and we can say this is the first number, this is the second number, this is the third number. 1, 2, 3, 4, 5, and then those first five terms. So what we're doing is we don't have to worry about arithmetic sequences at all anymore. Is if we have something in the exponential form, which looks very similar to a geometric sequence, we know the graph is going to look like this. It's going to fly really high. And what we're going to see later is that the opposite could happen. It could start really big and then gradually get closer and closer to zero. So this is what we call the exponential form. It looks very similar to a geometric sequence form. The only difference is instead of saying n minus 1 on the top, it says x on the top, okay? So if this is our form, even if it looks really similar, let's make sure we're mastering it. And if we want to graph this through tables, because it's an equation and not a sequence, we're going to do 0, 1, 2, 3, and 4. And if you plug 0 in, think that any number to the 0 power, so just think this is 4 to the 0, is 1. So if you plug in 0 to this equation, it's always going to be this outside number, okay? 4 to the 0 is 1, 1 times 10 is 10. So in this form, the outside number is the first term or the first number in your table. After that, this is the common ratio. So again, it's not the x-intercept here is 10. Sorry, the y-intercept. So the y-intercept is 0, 10. I know that looks like 10, 10. We do that. And the common ratio here is 4. So all this number tells us is from this, we're going to multiply by 4. So it's actually easier than our other tables because you don't have to constantly plug in the numbers into the equation. If you know that you just have to take the first number and multiply to 4 to get the next one, and then multiply to 4. Exponential means that number is quadrupling now every single time. So 10 times 4 is 40. Oops, times 4 a few times, and the number gets really big really quickly. I feel like maybe I did this in exact sequence before. It's not a big deal. But those are my numbers. And if I want to graph it, a lot of this set of lessons is all about how can we graph effectively with this freeform. And we really just want to look at what's the biggest number, and then how can I split this up so that we cover this. So here it's a little bit bigger than 2,500. So we can try to go up to something like 3,000. It goes up 20, the graphs I give you. So this isn't the easiest one. But I'm just going to go up by 200, okay? So each of these is going to be 200. And something that I like to do that I did a little quick last time is once I know what the scale is, I'm not going to put in every single number, right? I don't want to put in 200, 400, 600. That's kind of exhausting. Going by fives is a good way to do it. So if I know this is 200, 400, 600, 800, here's 1,000. And I'm going to now go up by 1,000s every 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Like that. Hopefully that makes sense. And then here I like to go by 1, and you can even go by 2 if you want to kind of make it, or sorry, 3 if you want to make it a little bigger, right? Just make sure they're all equally apart. And it starts off with all 3 of these values being less than 200, right? 0, 10, 0, 40, and 0, 160 are all under this first box. 4, 40, 160. Then it starts to go up much quicker. So 640. And then the next one is all the way up here. 2000. There you go. Now the next number would be way bigger, right? It's going to be 4 times this. So it's going to be like, it would be like 10,000. So if it asks you to do a fifth or a sixth, I guess it would be way, way higher. But again, that's that. That's a review. And now we're going to talk about the slight things that could change, that could make this different. Okay. So for number 2, we already notice the difference. And that's the easiest thing, like the best part of math. It's like, you shouldn't be surprised by the things that are added on, right? So right now, what we're adding on is a negative in my equation. And what we need to remember is this is the y-intercept or the first term of the sequence, right? We plug in 0 and we get this number. So we're starting negative here, okay? Unlike the other ones, we're now doing negatives. So we're gonna have to make sure we accommodate that in the graph. But this is my first term. And without having to overthink it, all I have to do to find the rest of my table is just keep multiplying -5 to 5. And when we do that, it's -25, -125, -625. So they're all negative, which shouldn't be surprising because we're multiplying a positive to a negative every single time, right? This times 5 times 5 times 5. So the number stays negative the entire way because the ratio is positive. And very quickly, we're not going to do any examples where this is negative, where the common ratio is negative, because if these numbers flipped, so imagine if it was -5, then 25, then -6, 125, the graph would be insane, be going up, and it's beyond the scope of this class or any high school math class. So just know that if you see a leading number that's negative, you'll see a positive on the inside, and that means that your entire graph is negative. But pretty much the exact same thing is happening, right? We're exponentially going down now instead of up. So you probably could do this on your own, but I think it's kind of cool. All we have to do is we still have our numbers 0, 1, 2, 3, and 4, but we have the negative quadrant instead. So to do that, I'm just going to do this. And again, if you want to graph it however you want, that's okay if you're a good grapher. But right now, I just want you to visualize that it's going to be completely negative, right? 0, 1, 2, 3, and 4. So both of these, you could think of this as like one big quadrant. I don't want to mess up my camera, but this is the upper quadrant. And this is a negative example, so we could just draw it all down. We have to get to -3,000. Last time I got all the way up to 4,000 using 200. So I can do the exact same thing here, right? The first one is down to -200, which means 5 boxes will give me -1,000. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And from there, I mean, I think this is pretty straightforward. It's just a little bit of work. We want to plug these in. So again, these first 3 values are all really close to my axis. 0, -5, 1, And I don't even know if I made this super accurate, but it's not a big deal. The big deal is that at 3, it's going to be way lower. So here, and then at 4, we're all the way down here. So if the graphing part is slow for you, it's just a good skill to practice. There's not much more I can say other than just be careful. So if it's negative, this is what your graph is going to look like. If it's positive, this is what your graph is going to look like. And I think the tables are also pretty straightforward. Good. So those are those. We have to tackle our last complication here, which is a fraction common ratio. So this part of it's going to be a little trickier, but I think it's not going to be too bad. So the fundamentals are going to stay the same. This is the first number, 0.81. And this tells you what you multiply this number to, right? So just as a quick review, this is so similar to geometric sequences, but if this number is a normal number like 2 or 4 or something, it's going to make 81 bigger, right? No matter what you plug in, as long as it's an integer, something greater than 1, the number increases. But if you multiply this by a fraction, so 1/3, for example, is our fraction here, the number goes down, right? So these common ratios that are fractions make the numbers smaller because you're dividing by 3 and not multiplying by 3. So if you see 1/3, think that you're taking 81 and dividing by 3. And that's not going to be too bad for this example. So let's just see what happens, right? We have 0, 1, 2, 3, and 4. And again, I try to really impress on you that using a table is a super effective way to graph anything. So we can pretty much figure out what this is going to look like. You could figure it out on your own. You don't even really need the rest of the lesson. You can figure this out by just filling out your tables and seeing for yourself what they look like. Yeah, I guess after saying that, no, but I'm going to do it. But all I have to do is take this number and keep dividing by 3. 27, 9, 3, and 1. So this is pretty straightforward, but what you should notice is that the opposite's happening. If the common ratio in this case was 3, and we started with 1, it would be 1 times 3 times 3 up. But because the common ratio is a fraction, it does the exact same thing in reverse. So if we're going to scale this, these are finally some smaller numbers. And we can make it go up by 5s to get to 100. And we're starting high and going low. It's not like the graph is flying down like a negative exponent graph would. Instead, it's going to shape the other way. So I said that kind of poorly, but let's sketch it in first. This is 81. Then we're all the way down to 27. Then we're down to 9. And then the next two are just in this lowest one. So what it really looks like is the other side of your quadratic, right? So we're here, and then we're easing into it. And you can imagine that it would go on forever, kind of like that, almost like some asymptotes as well. So these two together really do look like a quadratic, and I think that's pretty cool. So it's just flipped, okay? That's pretty much it. But what I wanted to cover now is what happens if we get some really fractiony examples. So this is the hardest we're going to get. And we're starting with 2. So last time we started with a pretty big common ratio, pretty big first number, 81. And that meant that we never got to the fractions, right? But here we're going to get to fractions really, really quickly. So we're already pros at the first steps. The first number in my sequence is 2. And then we see 1/2, so we divide by 2. So we get 2, 1. 1 divided by 2 is 1/2. Then 1/4, and then 1/8. So I can graph this the same way. I'm just going to change my scaling, okay? Where the biggest number needs to be 2. And since we have a lot of fractions, we can make my entire way up fractions, right? So we're going to go up by every 10 is 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 2. Does that make sense? I hope so. Then this would be 1/2. This would be 3/4. And we've created a pretty effective scale here. So what I think is really cool, what's really exciting for me, maybe hopefully for you, is that now that we draw this, even though it's fractiony, the exact same concept is happening, right? We'll see how we just kind of fly down, and the shape is the exact same as the one before. So we start with 0, 2. Then we have 1, 1. Then we have 2, 1/2. 3 is 1/4. Which would be halfway through 1/2, and then 1/8. I kind of dug myself a little hole here, but it's going to be like that. Okay? Because each of these represents a tenth. A tenth, yeah. So it'd be above it, actually. This is unimportant. Don't stress yourself out about this part. 1/8. So even though it was fractions, the scaling is still the exact same, right? Relative to each other, 2 is a much bigger number than 1/8. The same way that 81 is a much bigger number than 1. So even if you start getting into fraction territory, just make your scale fractiony, and the shape is really going to look the exact same. So that's it. I think we crushed it, and proud of you. Appreciate you. Woo.